Okay, so focus.
Taylor felt kind of bad because you totally bashed financial planners.
That wasn't my intention. I just was expressing that it wasn't what I wanted to do. All right, so the idea behind linear approximation is that, let's say that you have some crazy function like y equals square root of 3x cubed plus 2x to the negative 2 minus 5, I don't know, pi cosine x, okay? So this is going to give you some crazy curved graph like this, right?
Right.
Okay? The idea behind linear approximation is, let's say that we want to find out what the value of this equation is, not at an easy number like x equals 3, but we want to find the value of that equation at x equals 3.01. Okay? Well, what we're going to do is we're going to say, let's look at the tangent line at x equals 3, or whatever it is. And since the tangent line is really, really close to the curve at all of the points right around x equals 3, instead of plugging in x equals 3.01 into this whole crazy weird function, let's just plug x equals 3.01 into the equation for the tangent line. Okay? And the answer that we will get for that will not quite be what we expected to get, right? There'll be a very small difference, but it will be close. And since the equation for the tangent line is an easier equation than this thing right here, then in theory, that will save us some time.
Wrong.
Okay? Because, well, you'll see, all right?
So were you saying like close
So,
to enough?
yeah, so, right, so that's why it's called a linear approximation, okay? It's close, but it's not exact, all right? So, what it says up here is we have seen that a curve lies very close to its tangent line near the point of tangency. In fact, by zooming in toward a point on the graph of a differentiable function, we notice that the graph looks more and more like its tangent line. This observation is the basis for a method of finding approximate values of functions, okay? So the idea is that it might be easy to calculate a value f of a of a function. Like I said, if x equals 3, we might be able to plug that in and figure it out really easily, but difficult or even impossible to compute nearby values of f. So instead, we settle for the easily computed values of a linear function L, whose graph is the tangent line of f at a, okay? And so here's what we're going to do. You are familiar with the point slope form, I'm sure, right? Y equals the slope times x minus the x coordinate plus the y coordinate, right? Okay, in this class, the slope is what? The derivative. So we're going to rewrite this as y equals f prime of a, the derivative at that point, okay? X minus a, so this is, we're letting x1 equal a, okay? And then plus y1, but we're using function notation. So y1 would be what we get when we plug a into the function, so that would be f of a. Okay, and so that's where the formula for the tangent line approximation comes from. It is y equals the slope, so that's the value of the derivative at that point, times x minus the x coordinate plus the y coordinate. Okay, so that is called the linearization of f at a. And again, the idea is, let's say a equals 3, we might want to figure out what the value of the function is not at 3, but some value really close to that, so we can figure it out at like 3.01 instead, and it'll be really close. It'll be a approximation. All right? You're all going, yeah.
I like all that commie stuff on the board right there.
Totally, it's not, oh my God.
No, wait, I didn't write that here.
You know what you need to do? You need to travel.
I'm just
All right, so
the motherland. The motherland part is really what got me.
It's just,
I don't
what?
want.
Okay, find the linearization of the function f of x equals x plus 3 at a equals 1 and use it to approximate the numbers 3.98 and 4.05. Okay? Square root, sorry, yeah, square root of x plus 3. Okay, so to find the linearization at a equals 1, we're going to take the formula from the previous page, which is that the linearization is equal to f of a plus the value of the derivative of at a times x minus a. All right, and this time we're using a equals 1. Sure, man. No, not in, oh, the linearization formula? You could put this maybe in your notebook, sure. So what is f of a? When a equals 1, what's f of a?
I don't know.
2. Okay. What is f prime of a?
I don't know.
So let's take the derivative of the square root of x plus 3. So 1/2 x plus 3
Times 3.
to the
To the
negative
negative
1/2
times 1.
times the derivative of the second side, which is just 1. So if I want to find out what that is at x equals 1, 1 plus 3 is 4. What's 4 to the 1/2?
2.
So what's 4 to the negative 1/2?
1 over 2.
1 over 2, good. Because negative exponents just means you go 1 over the answer, okay? So this is going to be 1 over 2 times 1 over 2, which would be 1 over 4, all right? So our linearization formula for this is f of a was 2 plus 1/4 times x minus 1.
Wait, I thought we said it was 1 over 2.
Oh, but then we have to multiply that by 1/2.
Oh, okay.
Okay? So what we're going to do is we're going to use that formula to figure out what the square root of 3.98 is and what the square root of 4.05 is. Okay? So if I want to figure out what the square root of 3.98 is,
Wait, 5.
yeah,
Is A the slope?
So you got the.
no, A is the point, A is the x. And then plug them into the formula. Okay? All right, so if I'm starting with the square root of 3.98 and my formula was the square root of x plus 3, then what am I going to plug in for x? 0.98. And you see that 0.98 is very close in value to 1. That's why we can use this formula to approximate that.
So you just
Okay?
use the, wait,
So I'm going to plug 0.98 into here
why?
because that's going to give me an
Is
approximation
it
for...
because it's 3.98 minus
Yes,
3?
yes, right.
Okay.
Yeah, okay. So if I plug 0.98 into there, then the linear approximation of that is going to be 2 plus 1/4 times 0.98 minus 1, which you can just type into your old calculator and tell me is what? Hi, Taylor.
That was weird.
Looks like some other person named Taylor watching this.
Shout out!
Some person named Taylor in Mother Russia. What do you get? 1.995.
Wait, is that, so that's what Russian translates to?
No.
Oh.
That's her mother.
Right, it's her motherland. That's a sort of a Asian European thing where they call their countries the motherland. We don't have that same kind of. We just don't use that language.
I'm going to piss hole.
Okay, let's figure it out for now the square root of 4.05. So if I want to figure out the square root of 4.05, what do I use for my x?
4.05 minus 3.
4.05 minus 3, which would be 1.05. Okay, so that is, again, I'm going to use this formula right here, our linearization formula. So 2 plus 1/4 times 1.05 minus 1 equals,
If you think about math, it is so
what do you get?
2 plus
2.0125, okay? All right, another part of this is to understand whether these approximations are overestimates or underestimates. And so to do that, you need to be able to think about what the graph of the square root of x plus 3 is going to look like. What does that look like? Yeah, it's going to be shifted to the left 3, but it's going to be looking like this, right? So if I take the slope of the tangent line at a equals 1, then that's going to be something like this, correct? So when I choose 0.98, that's this one right here. So is this answer that I got an overestimate or an underestimate? Over, because my tangent line is above the graph. Okay? And this one is also going to be an overestimate because, again, my tangent line is above the graph. Okay? Here's my question. Okay, and then this is what we were just talking about. The linear approximation illustrated in figure 2. The linear approximation is illustrated in figure 2. We see that indeed the tangent line approximation is a good approximation, so these are very close to each other. Bless you. When x is near 1. We also see that our approximations are overestimates because the tangent line lies above the curve. Of course, a calculator could give us approximations for that, but the linear approximation gives an approximation over an entire interval. So there's your answer. What's your question?
Is that even bad?
So you use like point the 0.98 avoiding. Like I understand that's part. Why is it what it is?
Because the function that we made the linear approximation of was the square root of x plus 3. So if I want the square root of x plus 3 to equal the square root of 3.98, right, if I was to solve that for x, then I would find out that x equals 0.98. Okay? All right, so then we got some crazy stuff going on here. In the following table, we compare the estimates from the linear approximation in example 1 with the true values. Okay? Notice from this table and also from figure 2 that the tangent line approximation gives good estimates when x is close to 1, but the accuracy of the approximation deteriorates when x is farther away from 1. Okay? So this is the one that we know the actual answer of, and so these two are exactly the same. This one, if we did the linear approximation thingy like we did, we get 1.995, which is pretty close to 1.99499. But then if we did it for 0.9, we'd get 1.975, which is a little bit farther away, because the tangent line and the graph get gradually farther and farther away from each other, right?
Is that always going to be overestimated?
No, what would the graph look like for it to be an underestimate?
Parabola.
Right, a parabola or something like that, okay? Yeah, and then the tangent line would be here, and then our estimates would be below the actual values. All right? Okay, how good is the approximation that we obtained in example 1? The next example shows that by using a graphing calculator or a computer, we can determine an interval throughout which a linear approximation provides a specified level of accuracy. All right? Doesn't this look like fun?
Is that, so
It's
is
like
that,
the Charlie Brown thing.
is that how Alina writes her name?
I believe so, yeah.
Okay, I'm confused.
Uh-huh. Oh, be quiet back there. All right. Here we go. For what values of x? For what values of x is the linear approximation square root of x plus 3 approximately equals 7/4 plus x over 4 accurate to within 0.5? What about accuracy to within 0.1? Do you understand where they got this?
No.
This is what we got also.
They just simplified.
They just simplified it, okay? So this is the exact same thing that we came up with, but they just distributed the 1/4 and then combined the numbers, okay? So this is the answer that we came up with. All right, so if you want an accuracy to within 0.5 or a half, that means that the two functions should differ by less than 0.5, right? So that means if you subtract the original one, subtract the linear approximation from the original one, you should come up with an answer of less than 0.5. And the reason why they put it in absolute value is because it can be 0.5 more or 0.5 less, okay? So you remember from, I don't know, algebra or algebra 2, solving opposite value equations, you take this and you say it's less than, you know, right?
No,
Negative
I
and
thought
that.
you do like, so you solve out that one, and then
So-
you make everything inside.
So what you
opposite.
do with this, the missing piece is you would take this and say, that means this has to be in between negative 0.5 and positive 0.5. Does that make sense? That's how you'd start, just that's the inequality that you were taught to write from that. So all they did with this is they, what did they do? I don't know what they did. They got this stuff, they just like subtracted that from both sides, but somehow it's positive, so I don't know, just don't question that, it all works out, okay?
Why do we have to do that?
I don't know, just
It's
go
just
with
like
it.
showing us.
Go with it, yeah.
It's not like-
Okay, so this says that the linear approximation should lie between the curves obtained by shifting this curve right here upward and downward by amount of 0.5, and that makes sense, yes? Because you want to be within 0.5 of the correct answer, so as long as you take your original curve right here, if you move it up 0.5 or down 0.5, as long as you're in between there, you're going to be okay, right? So from here to here, that's where, if you're anywhere inside of that range, your linear approximation will be within 0.5 of the correct answer.
Cool.
Okay? All right? Okay, so then what they are doing is they are taking this linear approximation right here and setting it equal to the upper range of those things and solving. And when you do that, you find that you should be in between negative 2.6, or no, right here. If you're in between negative 1.1 and 3.9, then your linear approximation is going to be within a half, 0.5 of the real thing. Okay? All right, awesome. Don't kill the messenger. Oh my gosh, applications of physics.
No.
Okay, we might try some of these before we get into applications. All right. No differentials. Don't want to do that. Don't want to do differentials. Okay, so let's do just a couple of linear approximation problems on your own. Let's see your book. So we can do okay. You can do the first three. You can get Raina for that.
You have a lot more confidence in that.
Of course, the first
But
one
I
is
should.
red box.
Oh, get over it.